Okay, well, okay, it's Monday. Hallelujah. Heavenly Father, we thank you for this day and for your ministry of love to us. We thank you for caring so deeply, for leading us, for guiding us even when we don't realize that it's happening. You're a loving God, and you're a real good one. And so we thank you, Father. I pray this day that you would bless this class, those that are working on other stuff, that you would help them to do what they need to do. And be glorified by what we all do, Lord, internally. Not just what we do on the outside, the acts that we do, but internally. May you be delighted, Father, in Jesus' name. Amen. Okay, a couple things here. So, the article. For those that, well, it's not all to do with the article, it's to do with everything. Everything, this is big. So, taking finals, doing those things that are happening around, that are coming upon some of us suddenly. Like I found a lesson for today that I had overlooked until the last minute. So I could have freaked out when I found it. It was my choice not to. I don't like freaking out. I don't usually get any mileage from freaking out. The Bible tells us to be anxious for nothing, but by everything, by prayer and supplication. So it doesn't mean be anxious for nothing, say prayers, and then you go on your way and freak out. If you're freaking out, then it's a red flag.
Your tie is red.
It is, and Snoopy's on it. So it's happy all the time. This tie is happy. I mean, I could be sad, but I could put this tie on it. But it's really true. I mean, this is the one thing you can say, well, you know what I get out of being at Bible college, I got a lot of information that I guarantee you're gonna forget the good part of it in just a couple of years. You don't have to even be old to forget. But part of being here is learning that, wait a minute, if I'm freaking out, it's not God has a problem, but I've got one because he tells me in his word not to. And he tells us enough times in different ways to understand that he means it. So if we're doing what's contrary to what God says, then it's up to us to go to God and say, look, I'm doing this. And if it's something that you feel is out of your control, my grandfather had a violent temper, explosive and violent. His father had one worse than his, from what I understand. I never met my great-grandfather on that side, but he had a horrendous temper. So all my brother's brothers had the same kind of temper. One of them couldn't even get work. He could do anything and did it really well. He didn't drink, he didn't chase, he didn't smoke, but he just worked hard. But he had such a terrible temper, nobody could work with it. So I got that. I could blow up and not have somebody like poke, and I say, don't do that, poke, poke, don't do that, and then poke, poke, poke. No, I didn't have any pokes. I just went along all of a sudden. Well, replacing sheetrock, and I went, I didn't hit anybody, but, I couldn't control it. It happened before I knew. So I could say, God, I can't help myself. That's exactly right. I couldn't. God had to do something, and he did something, and he delivered me from that explosive temper. Now, I don't do things that just go to your sheet then. I'll get it later.
Okay.
Yeah. So I couldn't control it, but I asked him. So he didn't take it all away. I don't feed on violence. I don't feed on things that would feed that. Because God didn't take the wires out and pitch them. So there's no chance that could happen. But he's taught me to bring that under his leadership. Now I have a propensity to get intense real fast. Well, God, I've asked him to take it away more times than, for more years than anyone in this room been alive. And finally he let me know he's given me grace to bring it under his leadership. And then it doesn't get out of control. So if you're freaking out and you're not controlling it, red flag, okay, God, what do I do with this? You know what's happening to me. I've done this all my life. I've always done it under pressure. Or, it doesn't have to be freaking out for a test. It could be anything. Any propensity that you have that is inconsistent with God's word, he's the one to go to and say, oh man, Lord, something's got to be done with this. And I don't know what to do. Your word says not to do it. I'm doing it. How do we get this thing straightened out? And I believe God is able to do that. He did it for me. And if he says it so many times, then he wants us to come to him and say, look, we need to fix this. And so the ability to bring it under his leadership, to bring in my emotions under his leadership, even when I want to. Not only do I have emotions, but I want to. And he's helped me. And it's taken him a while to do that, to help me so I don't. So sometimes I just got to walk away from something. Sometimes I just got to go ahead and be gone somewhere and just seek him until I'm quiet. I've had to do that in the dorm. I had to spend 2 hours getting quiet to address somebody on an issue. Not a big issue, but I knew, because of who they were, if they pressed my buttons, I would respond. I didn't want to respond. That wouldn't help them, wouldn't help me. It took me 2 hours to get quiet enough. And it was not a big deal. But I was aware that I needed to be really quiet. And I needed to be there internally. Well, I found that when we seek him, in one instance, a guy that was so rude to me in the dorm, so rude. I don't think I've ever been treated so rudely. And I knew that I couldn't say anything, that I had to just walk away. And I did. He yelled at me as I walked away. I went up to my house. I wasn't living in the dorm, but I was the dean of men. So I went up to my house. And I thought, man, I felt like I'd been violated internally. And so I just went to prayer and said, Lord, I need to get this taken care of before I go to bed. And it took quite a while. It took a long time, actually. But finally I got to the place where I could ask God, Lord, I want you to forgive him. If he never asked you to forgive him, I want you to forgive him. I forgive him. I want you to forgive him, so he doesn't have to ask. Now, you could maybe question the theological aspect of that, but Jesus said, forgive them because they don't know what they're doing. I knew that was the right thing to do, and when I did that, I was as clear as a bell. I could meet him in the dorm the next day and not go and have to choke back anything. And that's the kind of freedom. It's not instantaneous. It's a choice to say, okay, I'm not gonna acquiesce to this. I'm not gonna do it. You tell me not to, Lord, I'm not gonna do it. And in tarrying before him until you get victory. Not an emotional feeling. I've had an emotional feeling. I thought that God did it. I found out, everybody's chagrin, that he didn't do it. It was very uncomfortable. Embarrassing. So I'm a little more serious. I don't want to trust the feeling, but I want to tarry before God until we've had some business taken care of. And I know you can. Now, I've been in the way a lot longer than you all have, so, and to go back, well, when I was your age, I wasn't even a Christian. Well, except Henry. But I didn't become a Christian until I was 29. So I started a little bit late. But I want to tell you, God has victory for us. And if God says something and we're living contrary to that, not like we're saying, no, God, I won't do it. It's just we find, man, I can't do that. Well, if you go to God and not just saying, Lord, I don't want to try to do this, you do it. But asking him for wisdom and for grace, I found him faithful. So this was not only about this class, but this is just about life. And life happens. It happens right now, it happens later. You don't get out of life when you leave here, you get deeper into it. And there's less time. If you think you don't have enough time to pray and seek God here, you'll never find it out there. It'll be hard. Well, you can find it, but it'll be harder. So, Article 1, just mentioning it. If you want, I can arrange to meet with people. If you want additional help with that, if you want to write a paragraph or write something on one and then turn it into me to see if you're on the right track, I'm happy to do that. But the deal was with Article 1, you read Wilson's article, the guy that is an evolutionist, and you read Wallace's article, who is a Christian. And Wallace states some principles in looking at arguments in his article. And so you take Wallace's principles in examining and apply them to what Wilson says. Now there are, I did the first two, so they don't count. But there's, I think, 12 more paragraphs in Wilson's article. I've broken them down into paragraphs so you can see. So out of the remaining, after the first two, from 3 down to 12 or however many they are, you can choose 4 of those, just any 4, to comment on, to point out using Wallace's evaluation tools and any that you have. We talked about a straw man, we talked about some other things, sweeping generalizations. We talked about things, well, you can use those as well to examine these art paragraphs and saying, okay, he's saying this, but he's using a sweeping generalization. It's not true. It feels like it might be true, but it's not accurate. To point out where Wilson is, yes?
According to your example, you want us to label which paragraph we're using.
Yes.
But let's say like he gives an argument that is later elaborated in another paragraph that's connected to that one. So which label would that go under?
So he starts in one and goes into another.
Yeah.
And is he using mechanisms in both of them?
I believe so.
Okay, well then there are 2 articles you could address.
Okay.
You could say he does this here, and then in the second one, you could say he started with this in the one above, and then he goes into this.
Okay.
And that's how they feed together. Yeah, good question. So if you have any questions about that, I'm gone Tuesday night. I'm around mostly Tuesday until I go to the prison. Mondays, I'm pretty free after this class. So I'd be happy to come down and meet with you after dinner, or whatnot, yeah?
So from the syllabus and what it looked like was you're picking apart the arguments, right? But what if you find a difference? So let's just say he used, in paragraph 4, he used an argument with a sweeping generalization, right? But then paragraph 5, he did another sweeping generalization. Is that okay to call out that even though he's using the same tactic? Or do you want 4 different tactics that he's using? Because I don't even know if we've gone over 4 different tactics. From what I can remember, I'd have to go back and reread notes and refresh.
Well, have you read Wallace?
Not yet, no.
Okay, well, Wallace gives a couple of them. We've gone over sweeping generalizations, a straw man argument, ad hominem, we've worked on that just in the early part of the class. But, so I wouldn't want you to do 4 that are just all sweeping generalizations.
What about 2? You prefer us not to do a repeat is what
Yeah,
you're saying? Okay,
yeah.
I follow you there.
Because I want you to think about it.
Yep, okay.
So if you can't get around that, then see me about it
Okay.
after that. Okay? Anything else? Anyone just do Friday?
Yes,
This Friday?
yes.
Second.
So we don't need to generalize into.
It kind of depends how you'd handle it. Sweeping generalizations are probably the easiest one to do, and I'd like you to at least do a couple of Wallace's arguments to evaluate. So let me take a look at that, I'll get back to you. Yep.
And how you want it formatted is simply just, so from what I gathered, you just want 4 examples with the 4 paragraphs and explanations. You don't want like an essay format with an introduction and conclusion, like it's not supposed to be that kind of paper,
No.
it's more just an assignment.
Yeah,
Okay.
yeah. So, and it's worth a couple hundred points. So you can write it like, oh, it's just an assignment, or you can step it up. Because that's, I'm looking for a thoughtful evaluation of what he says. You could write more, you could do a 5th one if you wanted to. It wouldn't hurt. I'm not requiring that. Okay. So that's that. This is number 13. I just turned that back. So you have 3 measures, sea level measures, inches of mercury, millibars, pounds per square inch. That's what those are. Pretty simple. And this one I said describe in great detail, in good detail. Meaning, I wanted good detail. Now, if this was a college class, I would expect you to have read all these pages to do this. But in reading your papers, you read until you got the part of an Android barometer and went, ah! And then you went on. So I talked about an Android barometer, but there were more things happening. So I didn't count. Again, I didn't count having what I would have put on, having read that whole section, the chapter. Okay, I'll just explain. So here's an Android barometer. And some of you rightly noted that these aren't, you can't just look at the barometer and say, oh, like you set it in the morning, you'd set this thing. I'd get this lined up in the morning. This little thing, I grew up with one in my house. My dad had it. I didn't care about what he did with it. I don't know that he did anything with it, but it's standing there in the hallway. It was just a little ornament. But you'd set this, okay, where it is today. You'd set where the air pressure is today, and you'd squeeze this down so this wouldn't move. And then this would move. And depending on where it moved, if the higher, you can see, the higher millibars, the more air pressure, the drier and fairer it would be. And the lower, it doesn't mean rain, it doesn't have to be. If it's set here, this is lower. Well, this doesn't mean rain, and it doesn't mean storm. It means it's going lower, it's going in the direction of rain. And if it goes in way the direction, it's going to get stormy. And you have to watch a barometer over a period of time. You can't just look at it and say, okay, because you've got to watch where it goes from where you set it. If I set it in the morning, it's going to go one way or another or stay about the same. So just because it starts to go one direction doesn't mean you have rain. It doesn't necessitate, if it moves from here to here, you may not have rain at all. In fact, if it goes down to here, you can expect rain to happen, but it may not be happening right now. If it goes down to here, you can expect stormy to happen. And here, It doesn't mean you won't get any moisture, but the likelihood is getting less and less. So it's not an absolute bang, this is the deal that's happening. So this is what I put. I wasn't expecting this. You can get full credit without this whole thing. When the barometer falls, it's indicating the entrance of a low pressure area. Now, if you just said low pressure looking at the barometer, I accepted that. But a low pressure area has come into wherever you are reading it. A low pressure area carries it converging counterclockwise inflowing surface winds, which it does, which you read later in the chapter. It talks about, I'm going to talk about that today as well. I didn't count off if you didn't include that. But that's one thing that it indicates. If I wanted the whole deal, you have a low pressure area, which means something's pushing the wind up, or pushing the air up. And you've got winds coming in, being drawn in like they would a heater. They're drawn in, they go up, and it causes the air to rise, and with rising air, clouds form, and precipitation can be expected. That's the strongest statement. If you say it's going to be rainy or stormy, you're wrong. It doesn't mean that. But precipitation, if a low pressure area is. So on the other hand, when the barometer rises, it indicates a high pressure area. High pressure area carries with it diverging clockwise winds, and we'll see that shortly. This generally causes air to sink, and with sinking air, clear skies and fair weather often follow. Because descending air is compressed and warm, cloud formation and precipitation are unlikely. So that's the drawn out. Nobody put that down. I didn't count off for having that thorough. I just wanted it in the answer to be that thorough. Okay? So you didn't get counted off, you didn't. But that's what it was. I was talking about the whole process. Okay, what is wind? Simply stated, wind is the result of horizontal differences in air pressure. Air flows from higher areas of higher pressure to lower pressure. What force is responsible for generating wind? Basically, I don't have these things on, do I? Basically, the unequal heating of the Earth's surface. The unequal heating of the Earth's surface. And so it's horizontal differences in air pressure. If you put that down, you got 2 points. If you got unequal heating of the Earth's surface, you got 4 more points, which is 6 points, which is what it's worth. If you got solar energy as the ultimate driving force of wind, you got 6 points, because that's the ultimate driving source of wind. Write a generalization. Simply, closest spaced isobars, the isobars are closer state, you got a steeper pressure gradient, you got greater wind. They're farther away, a weaker pressure gradient and light winds. That's. In other words, the closer isobars are spaced, the higher the winds that can be expected, and vice versa. The farther they are, the less. And lastly, a northeast wind is blowing from the northeast to the southwest. It's blowing across. So you've got north, east, so the wind is, 130. Wind is 130, it's blowing from 130 here down across to 630. So it's blowing southwest, going in a straight line from northeast to southwest. So it starts with, when they refer to where a wind is blowing, like a nor'easter is blowing from the northeast and it's blowing in a southwesterly direction. But they call it nor'easter because it's starting there. That's where it starts to blow. Okay. Is that okay? That's what we have, but I don't get it. Okay, this is air mass. Now I gave you a stack of stuff today. Air masses. We're gonna cover air masses, cyclones, anticyclones, which is what we're gonna get to talking about a barometer, and lightning formation, thunderstorms, or actually thunderstorms and lightning formation. We won't do all that today, but that's basically what we're gonna do. And there's only two more that I'll hand out if we get there, and one of is for tornadoes and hurricanes. So then we'll be done with this stuff. And I've got a study guide that hopefully I'll have out to you by Wednesday. And I have an extra credit assignment that I'll probably send out to you this afternoon for people that want to do that. So, this is not required, it's just, and I'd like you not to use, well, yeah. I'll think about that, okay. So air masses. Now we've been talking in this class about air packages, like little parcels of air, because it's easy to understand. It's easier to understand than trying to look at the whole spread deal. But this is talking about an air mass, like if you watch the Weather Channel or any weather on, usually they're talking about a large air mass, like a cold air mass is moving down from the north, and a warm air mass is moving up from the Gulf. And if that warm air mass is really warm, if it's collected a lot of moisture when it's moving, and these are moving fast, and one's really cold and one's really warm, you're going to get some action. You're going to get some weather action in there. So an air mass is a large body, usually 1,000 miles or more across, a couple miles thick, that's characterized by a similarity of temperature and moisture at any given altitude. So different altitudes may have different moisture contents and temperatures, but they're similar across a big span. They're not the same, they don't have to be exactly the same. One air mass is usually warmer, which means it's less dense. Colder or air mass is more dense. That's why in oreographic lifting, in frontal wedging, you have a dense cold air mass moving toward a warm air mass or vice versa, and the warm air mass is going to be clicked upward because the cold air is more dense, so it stays low. So you have this mass of air that's moving, and it is, usually 1,000 miles or more. I mean, they vary a lot. Air masses are modified as they move, but they also modify the weather over the areas which they move. Warm air mass in the winter may be colder than cold air mass in the summer. But between air masses, it's their relative density, warmth and coolness that matters. So it's not like this is cold and it meets the standard of cold. In the summer, a cold air mass is going to be warmer than it would be in the winter, but nonetheless, it's how that compares to the other air mass between warm and cold mass. So there's six, not six, there's four classifications of major air masses. You have maritime polar, continental polar, tropical, maritime tropical, and continental tropical. So there are four basic kinds, and you can see them designated here. You can see them on your sheet here, there. What they are: a maritime polar, which means it comes off here, the Siberia, which is cold land, and it goes across the Pacific, which is cool and wet. So it's a maritime, so it has to do with water. Continental, something that comes from North Canada and the Arctic. So it's cold and dry. It's not across a body of water. It doesn't pick up moisture when it travels. It's coming across land. It's cold and dry. The other one's cold and wet. And maritime polar is also from the North Atlantic, which is cold and wet. It comes off the Atlantic or the Pacific, either one. They're cold in the winter. It's wet. So they're all polar, cold, but maritime means they come off something wet. Continental, continental is not maritime, no, so maritime tropical, so coming across, so where the waters are much warmer, and it's coming off across the water. Equatorial Pacific, continental tropical, like out of Mexico, coming up Mexico. It's continental. It's across the continent, but it's coming from an area that's very warm. And that's tropical, and then maritime, which is all these. So you got two, maritime polar, continental polar, maritime tropical, continental tropical. So maritime and tropical, and one of them is polar, and one of them is tropical. So continental and maritime relate to the moisture content, the moisture in the air. And polar and tropical relate to temperature conditions. So you've got air that has a certain general moisture content, depending on altitude, but certain general follows certain characteristics with moisture, and it also here is involved in temperature. Cold, warm, continental, dry, maritime, wet. So moisture, continental is more dry, maritime is more wet. Temperature, polar is cold, tropical is warm. So in here's an illustration. Continental Arctic, so it's coming down, it's really cold, very dry. It's going over ice and snow, so it's cold and dry, coming down here. You get into Canada, continental polar. This is cold and dry. This is very cold and dry. This is cold and dry, so it's warmer here than it is here up in the latitudes, upper latitudes. Maritime polar, coming in from the north across the Atlantic and north across the Pacific. So these are air masses. Continental tropical, it's coming up out of Mexico up, and you find, well, the weather we find at least here going on with all tornadoes and stuff, this maritime tropical, which is warm and moist, when a warm and moist air hits the cold continental that's coming out from Canada or from the Arctic. So this is very, very warm and very, very moist. And it hits this very cold and dry. So cold and dry, much more dense. And the denser it is, it tends to be a little steeper. As far as an airflow, you can have like you can have it more shallow and steeper. Well, the steeper it is, where these things hit one another, this warm air is kicked up. And if it's kicked up really steeply, it's got a lot of moisture in it, and it's just kicked up really steeply, you have really severe storms. So, again, moisture content, temperature, condition, polar and tropical, you need to know that. So these influence the weather in North America, most particularly east of the Rockies. And about fronts. Fronts are the boundaries. The fronts are the parts that move. Like here is, right there. Okay. Fronts are boundaries that separate air masses of different densities. Warmer and colder. So it doesn't have to be tropical. It could be in a time, it could come across the Gulf of Mexico where the water yet hasn't heated up, tell it in a way that it does in the summer. So it's warm, but it's not as warm. And the air that's coming off Canadian coast, or Canada, is cold, but not like it would be in the winter. So you have these different, the fronts are still separating warm from cold, and the differential in the speeds, one front usually advances into another one. So some mixing does occur along the front surface, but for the most part, fronts retain their distinct identities. So cold air, warm air coming, cold air. If this warm air advances over cold air, it's kicked up here, and I showed you one of these the other day. It wasn't so, the wording wasn't so clear, but here you'd get rain, nimbostratus, altostratus, cirrostratus, so they're really high clouds, they're really, really high clouds. So if you're over here, and you look up in the sky and you see, oh man, I got cirrus clouds up here. And a little while later, you start to see cirrus clouds, but they're kind of thickening out. These are real wispy, real high. These aren't so high, and they're kind of getting thicker. And then you see altostratus, so they're getting even thicker here. And you can say, if you're here, and this is coming this way, this air is being moved up, the first thing you're going to see is cirrus if you're over here, and then you're going to see this, and then you're going to see this, and then you're going to see rain coming. So you can see what's going to happen. And here we have cold air coming, a warm air, a cold air front, a warm air front, and when they collide, it's going to kick. This warm air is going to be kicked up. And when this is steep like this and not shallow, you're going to get a lot heavier rainfall. The cooler, more dense air acts as a wedge, which lifting takes place. Cold fronts are on average about twice as steep as warm fronts, and cold fronts usually advance more rapidly than warm fronts. These two differences, the rate of movement and the steepness of slope, largely account for more violent nature, the violent nature of cold front weather as compared to warm fronts. Okay. The rate of movement and the steepness of the slope largely account for the more violent nature of cold front weather as compared to warm front weather. Because they're not always hitting one another. You can have a warm front move in, and things are nice. Because a cold front produces about the same amount of lifting as a warm front, but over a shorter distance, its precipitation has greater intensity and shorter duration. So, when it kicks up there, the intensity is going to be greater, but it's going to be typically lasting for a little bit less. There are four kinds of fronts, and I'm not going to talk about the stationary occluded. I might mention the occluded, but you just need to know warm and cold fronts. So with thunderstorms, all thunderstorms, every one of them, require warm, moist air, which is then lifted, when lifted, will release sufficient latent heat to provide buoyancy and instability to the air. So, the moisture in the air, you got a lot of moisture, you got more latent heat released. So the more release of latent heat, provides buoyancy or instability to the air, and it wants to rise. And when it rises, it cools. If it's got a lot of moisture in it, it cools as it go up, so it's got a lot of moisture to come down when it gets high enough, which is what's going to happen. They usually form along cold fronts where forceful lifting of maritime tropical air masses trigger development. So maritime tropical, warm air mass, full of moisture, cold fronts forcefully lift that maritime tropical air, and when they lift it up, then it can't hold the moisture that it has come with, so it has to condense and fall as it condenses. But instability and buoyancy are enhanced by high surface temperatures. Thunderstorms are most common in the afternoon and early evenings, usually in the hottest part of the day. So the sun has just warmed up everything. It doesn't just, when noon happens, the highest point, the sun's zenith, and then it starts declining. Temperature doesn't start, the sun is still hitting that thing, and so it's still warming. That's why it's common more in the afternoon and the early evening, which are the hottest part of the day. Such a cloud can be an enormous, 6 miles or more in diameter and 6 miles high, containing up to 500,000 tons of water. Our text states that some can reach up to 12 miles high, almost from here to Campton. That's just a cloud. And 500,000 tons of water. It's hard, you look out there where they're just white and fluffy like bunny tails. But they're bad actors if they want to be. Miles high, warm at the bottom, freezing at the top. They generate both tremendous updrafts and violent downdrafts, sometimes moving at speeds of 200 feet per second. So about 136 miles an hour, or upwards of 200 miles an hour, as warm air shoots up and rain shoots down. So I think I talked about this, but this was the German glider. Some men were in this German glider, and 5 pilots entered into a thunderhead, a violent cumulonimbus cloud, towering. Well, they glided into it. They were swept into the cloud's vertical air scuttle, and fearing their fragile aircraft would be torn apart, they bailed out and opened their parachutes. The updrafts immediately bore them to regions of freezing temperatures and pelting hail. They became human hailstones, falling, rising, and freezing. One idea about hailstone formation is that ice crystals are alternately warmed and then frozen as they move up and down. When they finally fell to Earth, 4 of them were frozen stiff. Only 1 survived. So it's amazing that 1. And I don't know how he got to land, because I would assume it would have torn up parachutes pretty well, because they were just. Characteristic of an anvil-like form of thunderhead occurs as upper level winds shear off the top of the rising cloud. So when you see a cloud that is flat on top, if it's a big towering cloud and it's flat on, that's the upper level winds that have sheared that thing off. And so this is a picture of what we have when you have a barometer and it has high pressure and low pressure. So you can see this low pressure, which means air is moving upward, and at the surface of this low pressure, where your barometer would be, you've got air that is circulating counterclockwise, and it's circulating in. It's being drawn in and kicked up. And as it's kicked up, you're going to get clouds. It's converging at the bottom. Down at the surface, you have converging winds, and at the top, you have diverging. They're going the other way. They're spreading out at the top. Now, this action above is driving this action below. What's happening aloft, this is called the loft. is generating what's happening below. But where you have a low pressure area, low pressure means air is being drawn up, it's diverging here, you get clouds, and it's counterclockwise moving in. On the other hand, a high pressure area where you've got air coming down, you've got convergence up here, divergent, so this is diverging, spreading out in a clockwise manner. Converging in at a counterclockwise, diverging out at a clockwise manner. So you can look at that. You've got an illustration in your book of the same thing. So this is where you have high pressure and low pressure. So that's why you watch your barometer to see which way it's going, and if it says it's low pressure, then you should be able to say, okay, it's low pressure, I've got converging winds on the surface coming in counterclockwise, being pushed up, and divergent winds up aloft, up above, which generate clouds, etc. There's a close relationship between surface disturbances and the airflow aloft. Airflow aloft plays an important role in maintaining cyclonic and anticyclonic circulation. So what's happening in the air way up plays an important part in maintaining these things. As long as divergence, outward flow, is aloft, that's divergence, would mean convergence at the surface, it would mean low pressure. Aloft is equal to or greater than the surface inflow, the low pressure, and its accompanying convergence, inward flow can be maintained. So as long as that's happening upward, it is equal to or greater than what's happening on the surface, you're going to continue to have that low pressure. The same thing would go to a high pressure. If it's not diverging up above, it's converging up above, making a high pressure area, you're going to have the same thing. Flow aloft will play a role as long as you can substitute convergence here. It works the same way. Convergence, which is an inward flow, aloft is equal to or greater than the surface divergence, then the high pressure area will accompany that divergence. So it's the same. It happens to both the high and the low pressure, that thing. It's not just one. In the upper level jet stream wind action, so this is the upper level. This is aloft. Wind divergence initiates upward air movement, reduced surface pressure, cyclonic or counterclockwise airflow, and can maintain or strengthen a low pressure area. Convergence, aloft, initiates downward air movement, forcing air down, increased surface air pressure, high pressure, anticyclonic or clockwise airflow, and can maintain or strengthen high pressure area. In all likelihood, upper level airflow that generates the surface wind, in all likelihood, it's the upper level airflow that generates the surface wind systems. So what you saw pictorially, this is just verbally. And it's the air aloft that, in all likelihood, generates these things. Okay, and I think I've talked about the wind, the jet stream, World War II, where they found out that where the bomber was flying in. So we didn't know that, but that is this. And we've got 5 minutes. This is not graded. Well, you have to put your name on these things and figure it out. Now, read it carefully. Read what the things are carefully. Don't just, you'll notice that what I have in this is adiabatic stuff. and you'll find that instead of 1,000 meters, it's 3. Where the 5 basic types of units. Yeah.
We're not gonna do that.
So you'll note that instead of 1,000 feet, 10 degrees every 1,000 feet is 10 degrees for every 3,000 feet. 3,000 feet is the same as 1,000 meters, but for the most part, that's what you have. So I use feet here instead of meters. So it changes, the dry rate is 10 degrees for every 3,000 feet, and the condensation level is at 6,000 feet. And so you have 10 degrees for every 3,000 feet dry rate, wet rate is 7 degrees. So figure out how this air starts at one side of the mountain and is pushed up to the top of the mountain and then down to the other side. What's temperature is it when it gets to the other side?